So welcome to the post-lunch session. So Professor Ramare will continue his lectures on the large sieve. Yeah, over to you. Yeah.
Exactly. Thank you. So to bring you back to the subject, we were looking at some sequences, maybe the sequence of primes in some interval. We were looking at the trigonometric polynomial that you saw in Keshav's talk. And we want to get information out of that. I told you that to sieve with a large sieve, you needed a local lower bound. And I talked about that last time. And that you needed a global lower bound that put all these values together. And that I had not proved. That's what I'm going to prove today. The proof is very short. Then I'll give you what I call Montgomery sieve, which is the way you sieve out of this inequality. Then I don't exactly know what I'm going to do. I'll do some history in between so that I can think what I'm going to do next. I'll prove that if you beat the factor 2, then you get, you show that there's no equal 0. I told you that in short. And most probably, I'll show you a very, maybe for you, strange way of proving the Brundtland inequality. Fairly fast, and that gives the optimal result as of now. So for the large sieve inequality, I'm going to prove it in two ways, and today is through Hilbertian stuff. So I'm going through something which I call Selberg's lemma. So what happens is that Selberg was at the Institute for Advanced Study. Bombiri was at the Institute for Advanced Study. And they talked together on the large sieve, especially. And in 1973, 1974, Bombiri gave a series of lectures in Paris and wrote a little booklet in which he says, here is this lemma by Selberg. But I don't know of any other place where Selberg has published it. So it's easier to call it Selberg's lemma. Selberg has done so many things, maybe he doesn't need a name more, but at least I recognize it in my head. So it's very abstract. So you take a Hilbert space, but it's really, I'm not going to do much with it. With a Hermitian product. But you'll see this space will disappear very fast. For F belonging to this space and a collection, a finite collection of functions belonging to this space, belonging to H, we have sum for I belonging to I of 1 upon mi, scalar product of f fi square less than L2 norm of f square, where mi, it is equal to the sum upon j belonging to I of L1 scalar product. Fi scalar phi scalar phi j. Okay. Okay, that's the lemma that will prove 1/2 of the large sieve inequality and almost everything. Yes, yes, for finite uses. It's just to tell you that the indices don't matter, it's just a finite family. So just imagine that this phi I are an orthonormal basis. Huh? If it's an orthonormal family, maybe not basis, then the mi, then phi is 1, phi j is 0 for j different from 0, so mi is 1. Yeah? Then when you get here is essentially the norm of f on the space generating by the phi, and you say that this norm of the projection is less than the norm of F. So it's an approximate Bessel inequality that I'm going to prove in 2 lines. The advantage that you can see immediately when you're doing analytic number theory is that you don't need exact orthogonality. Approximate orthogonality is enough, and approximate orthogonality on average is enough. So it's really a bonus. Oh, I put some, I'm not in LaTeX, sorry. And what else? Well, nothing more. Okay, proof. The proof is the proof of the Cauchy inequality. So you look at F minus sum of an I of lambda I phi, look at the norm, and you say that it's non-negative. Okay, nothing too difficult. And you expand this part. So it's F star minus twice real part of sum upon I of lambda I F phi, plus the sum of, okay, I and j, lambda j bar, phi phi j, or negative. Yes? And you would like a linear form, wait, what did I do? Yeah, you would like a linear form in the lambda I. You want to choose your lambda I optimally. And you're a bit, you're not happy because you have lambda I, which is multiplied by lambda j. So you want to separate them. But you know how to do that. I mean, or you should know. You use lambda j bar is less than lambda I square plus lambda j square, which you put inside. And what you get is simply norm of F2 minus twice real part of sum upon I of lambda I bar F phi plus sum upon I of lambda I square. And I put absolute value because I wanted to an upper bound of phi phi j, non-negative. And here, there's a sum upon j here that I forgot. This one is mi. Okay? And now you have to choose your lambda I optimally. Well, here, choose lambda I equal f scalar phi upon mi. So that this one, it's I here. So that this one and this one gets exactly 1 times this one, this 2 disappears, and you get 1, and you get this inequality. Okay? Honestly, it's difficult to have a simpler proof than this one. But it's very interesting, because since this lemma is crucial, you can see really what we are doing. It's an orthonormal projection that you're trying to control. You're trying to control almost orthogonality. Maybe you should be more precise about this almost orthogonality, take care of a second term. I mean, you can get lots of ideas out of that. So theorem, what I call the large sieve inequality. I'll tell you later why the denomination large sieve comes in. The large sieve inequality. So let X be a finite set of the point, the torus. Set delta equal the minimum of distance to the nearest integer of x minus x prime for x prime belonging to my set x, and of course different. Okay? You're on the torus here. Up, you're here. And you have point x, let's say x1, x2, x3, x4. Okay? What I assume is that they are spaced enough. I'm assuming that this delta is positive, and the bigger it is, the stronger, I mean, the more precise is going to be my inequality. Yeah? We have, it's forcibly finite. If delta is positive, you can have at most 1 upon delta or 1 upon delta minus 1 and point. Yeah. Sum for x belonging to capital X of, good question, sum of un, e, n, x less than n minus 1 plus delta minus 1, sum of un squared. Okay? I forgot to say, we have for every complex sequence un, of length n, we have this inequality. Okay? So that's the global inequality. This one is my Fourier polynomial at x, and I can give an upper bound for the global average of these values. And the proof should not take me long. Any idea how I should do? Sorry? It's delta. I mean, delta minus 1 is an upper bound for the size of x, in fact. Otherwise, it's a good idea to check. So you see, we have this lemma here, and we want to convert it into that lemma. So we want f, that's going to be my sequence un. Phi I is going to be exponential nx for n varying, and x index x is my index I. Okay? So the product f times nx is going to be the value of my trigonometric polynomial. And let's hope I can control this one. So set define phi, no, f first. F is a sequence un, n less than n. And then if I do that, I'm going to have some little problem. I have to handle some error terms, and I don't want to handle error terms. So I've given you an excellent manner of getting rid of error terms before. So recall that C, yes, C minus M delta is an upper bound for the.
Don't use delta. Delta is the spacing.
Yes. Okay, I can use another one, but it's going to be the same. That's why, but it's true. In general, it is not exactly the same. Give me a letter. Delta prime. Okay, delta prime. Oh, delta prime. For the characteristic function of the interval minus m, that is such that its Fourier transform equals 0 when u is larger than delta prime. Huh? And we had also the property that the value in 0 of u is equal to 2m plus delta minus 1. That's the last lemma I gave last time. It's built out of the Berling-Selberg function. And the Fourier transform is defined like Rita Brata did this morning, so same normalization. Because, anyway. Okay, so instead of, you see here, it's a function un times 0. Okay, so that's a characteristic function here. To be very precise, I've defined this function because I've given you very explicit formulae with minus m, and I need the interval 1, n. So you have to do a shift. You have to put m equal integer part of n minus 1 by 2, I think, and look at c of minus mm delta of n of t plus m. Okay. That's an upper bound for the characteristic function of 1n. Yes. Which also has the Fourier transform is just by multiplying by exponential Tm. So the same property applies here. Okay. And so what I'm going to do, I'm going to change that. I'm going to take f to be un, I will call it b of t, because I don't want to take all my indices. I'm back to my delta, I'm sorry. So un times b, no, it's better, over b of n. That's my sequence, but square root of b of n, sorry. Okay. So b of n, when un is larger, is non-zero, the support, bn is a bit larger than 1. Okay. So you divide by something which is slightly less than 1, but you'll multiply by the counterpart. And phi x of phi x is a sequence E and x times C times B of n. This time over Z. This one also over Z. Don't worry if you divide by something. Outside of 1n, this one is 0, so you can divide by whatever you want. Okay, so can we control the scalar product of this one? What do you think about phi x scalar phi x prime? Is a sum for n in Z, square root, sorry, of Bn Enx E minus n x prime. Free meal for who is able to evaluate this. If x different from x prime, you should be able to give me the value. It is equal to the sum for n in Z of Bn En x minus x prime. And you know everything about Poisson summation formula. Or at least at the end of this week, you should know everything about Poisson summation formula. This one is a sum for L belonging to Z of B hat of L plus x minus x prime. Okay? Fourier transform, that's Poisson. Summation formula. Okay. Now these are integers. You have L equal to 0, L equal to 1, L equal to 2. 0 plus a bit of something. If x is different from x prime, this little something is larger than delta. Okay? But the support of this Fourier transform is inside delta. So if x is different from x prime, this function is 0 at L equal to 0, L equal to 1, and so on. That's magic, I agree. Equals 0 when L is different from when x is different from x prime. It is equal to when x equal to x prime, you have b hat of 0. B hat of 0, that's my value, 2n minus 1, which is about 2n plus delta minus 1, plus delta minus 1. That's n plus delta minus 1 when x equal x prime. If you look carefully, really look, you will see that you can put n minus 1. We don't care, it has no influence. It's just that it is optimal in some case. But this part you should see. Yeah. I've built a family of functions that is orthonormal. Okay, if you have that, you see that mx is equal to n plus delta minus 1, because it is the scalar product of phi x plus all the other scalar products that are 0. So it is this one. And Selberg's lemma gives me the sum for x in my big X of f scalar phi x square less than n plus delta minus 1, sum of un upon square root of bn squared. That's my L2 norm of f. This one is less than sum of un squared, so I'm happy. And I did a bad thing with the other one. No. For the other one, this is a scalar product, f scalar phi x. Look at what it is. Sum for n of un upon square root of bn times square root of bn enx. My square root of bn cancels out. I get un enx. Okay? So there's a part of magic with this bn. You can easily remove that, remove this bn, just take phi of x equal enx on a finite interval, compute that, you'll see that the scalar product, it is not 0, but it's not so big, at least on average, and you'll prove something similar, except that instead of having delta minus 1, you'll have delta minus 1 times log or 1 upon delta or something like that. So it will be a bit weaker, but really this smoothing part is very helpful, but it's not the main part of the game. Okay? The main part is really Selberg's lemma, approximate Bessel inequality. But since it's so nice to have this tool, you see the error term just disappeared. It also disappeared because I wanted only an upper bound, and I didn't care about something more precise. See, at the end, I could save this. I divide by the square root of bn. I could try to save this guy. I don't care. Okay. Okay. So Now, I want to show you the main form that we are going to use. You saw in the previous talks that when we look at the circle method, we are very interested in the point A by Q. Till also my last talk, I was interested in the point A by Q. So we want to see what's happening on the point A by Q. We have sum for Q less than capital Q, sum for A mod star Q. For Rita Brata is a sum for A Q star of sum upon n less than n of un en A by Q, where less than n plus Q square sum of un square. Okay? So who can prove that after a good meal? Who can prove this one out of that one? Out of this one? No, you're not allowed. So what is the set X? You know, I'm not so young, so you have to speak a bit more loudly. Which is A by Q. A bit more precise, is a set of A by Q, Q less than capital Q, and A prime to Q. So that's the Fourier sequence that you saw in Fourier's talk, that you saw in Interpreta's talk. No, in Keshav's talk. But you'll see it this week, you'll see it constantly. What is the spacing between 2 points? I mean, what is the minimum distance between 2 points? A by Q minus A prime by Q prime. Yes. Cool. So that's my delta. I mean, it should be 1 upon Q minus 1, to be honest, exactly. But that's my delta. So here I had delta minus 1, which gives me Q square here. I don't have anything to do. It's done. Okay? Here, in everything I do, you'll very often see it written as A by Q. Okay, now I don't want to go too much into general sieve stuff, but I just want to show you a lemma in a simple theorem in a simple situation, which I call Montgomery's sieve. Not everyone does that, but I think it's because people don't know exactly the history, that they don't know how to call it. So on the safe side, they don't give any name. I have the feeling that it's absolutely due to Montgomery and that it can have his name. So let every prime P less than some capital Q, select a set Kp inside Z by Pz. That's the integer you want to keep. If you want to sieve the primes, you say I'm going to keep all the integers that are not 0 modulo P. So that's, I know that are not divisible by this P. Let Z be the set of integers in an interval m plus 1, m plus n. Integers, I need a name, n, that are such that n belong to kp, sorry, for every p less than q, n belongs to kp. It's a bit annoying when we referee papers by younger people, usually. Sometimes you write in the way you think. So for instance, you write n belongs to kp for every p. Okay. And you put the quantifier in the reverse order. I do the same because we think in the same manner. Still, it's easier for a reader to know who depends of what. So please reverse the order when you can. Then Z, the cardinality of Z, Z, the set, okay, number. The cardinality of Z is less than n plus q square upon G star q, and G star q is a sum for q less than capital Q of mu square q, product for p divides q of p divided by cardinality of kp minus 1. That what is the bound? The generic bound that is given by Montgomery. I'm going to show you how you apply that for the primes immediately. Just I want to tell you one thing about the problem that Keshav proposed yesterday. Yesterday, the problem was to know whether we could get a bigger spacing in case we have only square free Q. I mean, one part of the problem was that. Assume you restrict your set to square free Q. You see that in this bound, only square free Q are appearing. Can you decrease this one? Or can you improve a bit in some sense or some other sense? The cardinality of this set. I'm not as good as LaTeX. It's a capital K, index P, cardinality. P upon that, minus 1. Oh, cool. Okay, for the primes. You know, I want to have a look at the Brun-Titchmarsh inequality. Really, that's my friend. For the primes, Kp equals Z by Pz star, which is simply Z by Pz minus the set 0. And the cardinality of Kp is equal to P minus 1. Oh, not do anything too difficult. So P upon Kp minus 1 is equal to 1 upon P minus 1. So you discover that G star Q is equal to sum for Q less than capital Q of mu square Q upon phi of Q. Okay? Because it's a product of P minus 1 for P divides Q. So it's 1 upon phi of Q. And this one, let us see whether you remember. It's larger than what? Huh? No. You're not allowed to answer. Yes, like Q. Okay, we are in the same position and the proof I did yesterday. Okay, except that this one is in general. So for the twin primes, because everyone loves the twin primes, and I do. What is the set you're going to take for the twin primes? So you have, it's an integer n, so that n is not divisible by p less than q, and n plus 2 is not divisible by p. Yeah? So for p equal to 2, you take k2 equals simply the set 1. Because the class of 0 and minus 2 are the same. So for p larger than 3, you take kp to be z by pz, and you remove the class 0 and minus 2. So the cardinality, I think you can guess what it is. It's p minus 2. Of course, p minus 2 doesn't work for p equal to 2. So G star of Q is the sum for Q less than capital Q of mu square Q upon, times, P upon Kp minus 1 equal 2 upon P minus 2. P minus Kp it's 2. P minus Kp it's 2 divided by times the product for P divides Q, P different from 2, sorry, of 2 upon P minus 2. Okay. And for P equal to 2, it's 1. Okay. Who has an idea of the size of this G function? I don't have any magic proof like I did for G of Z, but who can get an ID? Just like that. Yes, why? How would you explain that? Oh? Yeah, but just erase that from your mind. No, just imagine, get the order of magnitude that it's P and not P minus 2. Yeah? So it's 2 to the omega Q divided by Q. Okay? The square for integers is a positive density. You can forget this condition. 2 to the omega Q is almost a divisor function. It's the same order, it behaves in the same manner. So it's essentially the number of divisor d of Q divided by Q. Okay? This one looks like the sum for d of Q upon Q. And that either you know that it is log square, either you remark that it looks like the sum upon 1 upon h square. Because when you develop, you get the number of divisors here. So that's log x, log square, log square, log square. We have lots of theorems that prove that this one is equal to log square with explicit error term, with blah, 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 blah. But simply you should imagine the order. Okay, just before the stop, I'm going to tell you a bit about why the large sieve and what is the general confusion on this denomination. There's a general confusion because it is not adapted at all. What happened is that in 1941, Linnik, who was a great mathematician coming from probability, decided to have a look at the primes for which the least quadratic non-residue was small. You know, modulo prime, you have squares and non-squares, and you believe that the first non-square is less than log p, maybe twice log p. Okay. So you believe that it's extremely small. We are not able to prove that. And Linnik wanted to use some dispersion, some L2 estimate on average to improve on that. And he proved that for almost all primes, this quadratic residue, quadratic non-residue, is less than p to the epsilon. Okay. So if you want to sieve the square on the non-square, modulo p, you have p minus 1 by 2 non-square, and p plus 1 by 2 square. Okay? So you want to get rid of the square, and you want to keep only the non-square. Just imagine if it's a sieve, that lets half of the thing out and keep half of the thing. When we have primes, we let everything go except the class we remove only the class 0. So we let very few things go through. Okay. When you have the twin primes, you have only 2 holes for each prime. No? So you remove very, very few things. For linear, you remove p plus 1 by 2 things. That's why it was called large sieve. Okay? But at that time, you didn't have any trigonometric polynomial, you didn't have an inequality, it was a result. So the paper of Linik, when you translate the title from Russian to different languages, it is the large sieve. Okay. Then people were fascinated by this result. And by some trigonometric polynomials were introduced. And then a more general version like this one was found. And we discovered that we could sieve directly from that to that. So now we have 2 things. You have the large sieve inequality and how you use the large sieve inequality for sieving purpose. All of that we call the large sieve. Okay. And tomorrow I'm going to show you another proof, and I'm still going to tell you that it's the large sieve, though you won't find this inequality. Okay. But it's going to be the same spirit. You'll see clearly that it's the same spirit. That's all, and we can stop. Yeah. Thank you. No, if you clap, it means that you don't come for the second part. You know, in classical music in France, between 2 pieces, the players, they stop. And you should not clap. You know, you should let the artist concentrate. Huh?
2 pieces of the same set.
Yeah, 2 pieces of the same set. Yeah, between the first movement and the second movement. You know? But it's always tempting to. So it's about the same. A larger sieve exists. It has been invented by Gallagher. We don't understand how it works, but you can sieve. Essentially, this sieve, the large sieve, is valid till density square root of n. So you can sieve out the squares. I have written several papers saying how you could use a sieve to get properties on the squares. But if you want to sieve the cubes, the sieve tells you that you have square root of n cubes, which is not a great thing. But the Gallagher sieve can go up to getting a finite number of elements. It's a very tiny stuff. We don't exactly know it works. It works. We don't have any proper setup for that. Christian Erholst from Graz in Austria has studied that a lot because he uses it a lot in combinatorial number theory. So he has tried a lot to put some context and some more things around that. But so you can look at the larger sieve of Gallagher. It's a very short paper for 4 or 5 pages. It gives beautiful results, and it still needs to be explained, according to me. We don't need how to generalize it. We don't. It's just something that works. Okay, I'm first going to show you something fun. So let us call it divertimento. You know, I like the Brun-Titchmarsh inequality. No, first, if you want to do some exercise because you find that you're getting bored or you definitely want to get muscles in sieve theory, get this theorem and prove that the number of primes with the added congruence condition congruent to 1 modulo 3. Just add one congruence condition and get the proper upper bound. I did it only for the congruence condition, trivial congruence condition modulo 1. Add a congruence condition. You'll see you have to tweak things, and maybe at the end of this lecture, I'll give you some a bit of materials that you may use to compute the density. Okay, so first I want to show you something. Okay, let me start with a theorem that's which is due to Jan Christoph Lagerpushta. I'm before, and myself. We have a number of primes in an interval m plus n of 1 is less than 2n upon log n. You're getting used to this 2n upon log n that you see and see and see again, plus 3.53 when n is large enough. Okay? That's the best thing we've been able to do to beat the factor 2 up to now. So we're looking at the second order term. Okay? Selberg got 291. We got 353. Once we got that, you can imagine that I spent at least 1 year doing a better proof and sweating and sweating and sweating. And finally, I got a wonderful proof, extremely conceptual, rather different from this one, with long computations to get the constant. And then you have the constant that pops out of your computer. It's 3.5307. I did not publish the paper. I don't know, there seemed to be something blocked, but really blocked even at this level. Okay, but I'm going to give you a bit of one of the ideas that goes here, because otherwise you won't be able to read this paper. And you'll see it's lots of fun. And also it's good for this auditorium because we are looking at the Ramanujan sum. CQ of n is a Ramanujan sum. I'm already showed how you can use that. And f of n, you see it's going to be the characteristic functions of the primes in my interval m plus 1, mn. m plus n. That's the kind of people we want. And if you look at the scalar product f of n times CQ, okay, scalar product like this one. So it's the sum upon n in my interval of f of n, CQ of n. Can you guess what it is? So I'm going to assume that Q is less than square root n, which is less than n. Huh? So what is the value of CQ of n? N is a prime, huh? Because otherwise f of n equal to 0. N is a prime which is larger than m. Huh? It is prime to Q. So what is the value of this one? A bit better? Mu Q. You're still not allowed to answer. This one is mu of Q times the sum of f of n. Yeah? Okay. Now you know Selberg's lemma. I told you Selberg's lemma is the heart of this story. My smoothing function that I added is just just so that it looks better, but the heart is really Selberg's lemma. So you have a candidate basis here. So what you can do is that you can look at phi q is going to be CQ divided by square root of phi of q. And what I want to say is that define M of Q is a sum of Q prime less than capital Q of scalar product of CQ of CQ prime 1 upon square root of phi of Q prime. Okay. We have the sum for Q less than Q of 1 upon MQ F CQ upon square root of phi of Q square less than L2 norm of F, which is the number of points. Huh? But this one, you know, we've just computed this one. This one is, let me give a name to this one. I did a mistake with my Z, so let me call it Y. So this one is equal to Y mu of Q upon phi of Q. So what we have is the sum for Q less than Q of Y square, comes here, mu square Q upon phi of Q, 1 upon less than Y times the maximum of MQ for Q less than capital Q. Yes? I had a 1 upon MQ. I'm going to take the maximum because I know they are all going to be of the same size. So finally, what you get, because you can simplify by Y, you have G of Q times Y is less than, I forgot something somewhere. I must have forgotten something somewhere. Because if I get the number of prime less than 1, it's going to be very less. I have a... What is happening? That's my max of M of Q that I forgot. Is less than the max of M of Q for Q less than Q, which is max for Q less than Q of sum for Q prime less than Q of sum upon N in my interval n plus n of CQ of n, CQ prime of n upon phi of Q, square root of phi of Q prime. Okay. And this one, when Q equal to Q prime, is going to be equal to n. What did I do? No, I did a mistake. Sorry. No, it's okay. So what can you say about this one? Sum for Mn, M plus n of PQ of n, PQ prime of n. the scalar product of my two things. Well, lazy way, I'm going to show you a lazy way, and then I'll let you do the more clever way. It's to say that to expand in terms of exponential sum. Sum for n plus n of E n A by Q minus A prime by Q prime. I've just said that CQ of n is a sum upon invertible residue. Yeah? So if A by Q equal A by Q prime, no cancellation, capital N. So it gives you capital N times the number of A, capital N times phi of Q. You divide it by square root of 5Q square. So you divide it by phi of Q. So the main term, the diagonal, the term for A by Q equal A prime by Q prime is equal to N plus zero term. Okay? The other ones amount will give you a big O of something. If you're not clever, it will give you a big O of Q to the 4. If you're more clever, it will give you a big O of Q square log Q. If you're even more clever, it will give you a big O of Q square. Okay? So M of Q is equal to N plus big O, let me log Q. Yeah? So I get my number of primes is less than N plus Q square log Q divided by G of Q. You see, it's kind of magic. I just pulled out a special set of functions, Ramanujan sum. They behave very nicely with respect to the prime. I use Selbach's inequality and proof. The large Sieve inequality has disappeared. You've gone one step closer to the proof. And if you go into this proof, you have a bit of preliminary sieving, you have a bit of twitching, you get something like that. Okay, that's what. Yeah. Okay. Now let me do some. I told you it's beating the factor 2 in the Brundtland march would let you show that there's no Ziegel zero. So I need to show you that. And the proof is not due to Balasubramanian, sorry. It's due to Ramachandra Shankaranarayanan. And Srinivas. So maybe you can, you'll check the proofs that I give. I don't know, there's some long names that I can remember, but this one needs concentration. Okay, so the theorem, I need to write it precisely because it's always too easy to do stupid things. There exist don't worry about effective constants. It's only if you understand why I put that it's interesting. If you don't see why, just forget it. C3 and C4 positive, such that, oh, I did a mistake here, for K larger than C4, the following conditions are equivalent. there exists a constant psi positive such that for every L mod Q mod K, the number of primes less than X. Okay. Primes congruent to L modulo K of 1 is less than 2 minus psi X upon log X of phi of K log X with X equal Q to the C4 and 2 for every character modulo K, we have L1 chi for every character chi modulo K, L1 chi larger than 1 upon log K, which is the dream of many persons in analytic number theory to show that L1 chi is larger than 1 upon log K. We even believe that it could be of size 1 upon log K. By the way, I can give you another problem which is fascinating. So we have lots of problems to show that L1 chi is not too small. Okay, but so you may think the difficulty is really to show that it's not 0. But we are not able to show that L1 chi is little o of log K. We're not even able to show that it is not too big. We believe that the problem is when it's too small, but even the other one we are not able to. Okay, I'm going to prove that 1 implies 2, because 2 implies 1 is another technique, and what is interesting is really from this one to that one. So the sum for the primes P less than X, so that chi of P equal minus 1, yes, of 1 is less than, I hope this is a good one, phi of P, which is P minus 1. Yeah, I put phi of P, but it, no, it's phi of K, sorry. Phi of K by 2 times 2 minus psi X upon log X upon phi of K log X. So it is, and this one is equal to 1 minus psi by 2 X upon log X. Yes? Because you have a phi of K by 2 classes such that chi of P could be equal to something which has value minus 1. Yeah? So you deduce that the sum for P less than X and chi of P equal to 1 of 1 is larger than psi by 2 minus little o of 1 X upon log X. Yes, you know the number of primes is X upon log X plus little o of 1, so you deduce. So you have a positive proportion of primes, so that chi of P is equal to 1. Already when you know that there's a positive proportion of primes that chi of P is equal to 1, you believe that you'll be able to get a lower bound for L1 chi. Now, what is the quality of this lower bound? You know that you're going to do better than what you had before, but can you go up to the best one? That's the idea. I mean, that's the end of the idea. So what we say is that we consider a usual function G of n is 1 star chi of n. Okay. It's a multiplicative function. It's a function that you'll see occurring very often in this kind of problem. And the function g is non-negative. That's one of the fun part, of the essential part. G of p is equal of 1 plus chi of p. It is non-negative. And if chi of p is equal to 1, it's even larger than 2. G of p to the k, well, you see what it is 1 plus chi of p square, chi of p square plus chi of p to the k. So if chi of p is 1 or 0, this one is non-negative, so it's non-negative. If chi of p is minus 1, it's 1, 0, 1, 0. You can also say that 1 star chi is in fact the number of ideals in a quadratic number field. Being a number of ideal, it's quite normal that it should be non-negative. So geometrically, this has some explanation, like many positivity properties. Okay, then we are going to remember that, that the proof is given by one of the authors is Ramachandra. Because of the next equation I'm going to write. Oh. Cool. Okay, Srinivas. Srinivas. Okay. We consider an integral 2 plus I infinity. I forgot what. G of S. G of S is going to be the function theta of S times theta of S times LS chi, which is this one. Sum of G of n upon n to the S and larger than 1. Huh? So we look at G of S plus 1 gamma of S E x by S to 2x S minus xs ds. Yes. And you put 1 upon 2 pi because you want to shift your integration and okay. That's here's the guy. Have a look at it. What can you say about this guy? First, you can expand this one. When I put 1, I could put 1. I mean, anyway, half place of conversion. But since I put a plus 1, I can. So you can. Yes. First, you can expand this in the Dirichlet series, and if you know what is called the Cahen-Mellin formula that gives you the Mellin transform of gamma of S. You know that this one is sum for n larger than 1 of G of n E minus n upon 2x minus E n by x. Should be that. That's what my sheet of paper tells me. Yes, except that it's plus 1, so it's G of n by n. And then you think, okay, I have to do something very, very clever because I want something very precise. No. You just say that it is larger than, for the integer between x and 2x, p and 2p, just take these primes, G of p by p. When p is between these two bounds, This one is positive, larger than 1 upon E, it's a constant. So it's larger than something. You can remove every integer because I told you that, this function is non-negative, okay? And P, you can remove its X. So it's larger than the, 1 upon X, the sum for P, and chi of P equal 1, and this one is 1. Huh? And this one is larger by my hypothesis over there, that psi upon X, X upon log X. Okay? I got psi upon log X. Okay, and now you see when you see this kind of integral, what are you going to do? No. What are you going to do with this integral? Type it in LaTeX, yes, okay. But after having typed it in LaTeX. Oh, simpler. Saddle point method. No, simpler than that. I mean, when you have a Mellin transform, when you want to compute the number of primes, for instance, you express as a Mellin transform, then you shift the line of integration. Yeah? So you look at the poles that will give you the main contribution. That's simpler than the saddle point method. So, okay. Yeah, I should put it here. Ah, no, I need the statement. The integral from 1 minus infinity of 1 plus I infinity of G of S plus 1, gamma of S, 2x to the S minus x to the S ds, 1 upon 2 pi, 2I pi. Let me go to the line, what is going to be fun? I'm going to go to the line minus 1/4, because I want a pole here. So in S equal to 0, because of this kernel, at S equal to 0, it kills the pole of gamma of S. But you still have a pole because of zeta. So this one, in zeta, you get L1 chi plus 1 upon 2I pi. Integral, it's minus 1/4 minus I infinity to minus 1/4 plus I infinity of G of S plus 1 up gamma of S 2x to the S minus x to the S ds. Okay? I'm not going to do the precise evaluation. I'm not just going to tell you what happens. What happens is that gamma of S has exponential decay when it goes up. Yeah? On the vertical strip on top. So essentially, you can believe that this integral is a bounded integral. Also because G of S plus 1, product of 12 functions, it grows at most polynomial. Yes. And here, so you're going to save an x to the minus 1/4. So you're going to save a power of x. Remember that the lower bound you have is 1 upon log x. And this one, sorry, here there's an x. Yeah. Okay. No, there's not. Wait. No, it's okay. So you're going to save an x, but then you have to see what is the dependence in Q, because you're in K, in the conductor. So it's a story of the dependence in the conductor. But you know that it's going to be polynomial in the conductor. So if you put take X large enough in terms of a polynomial of the conductor, K to some high power, this one is going to be less than this one. This one, you know that it's at least 1 upon K to 1 upon square root of K. But at some point of time, this one will be smaller. Okay? So what you have, G of S plus 1, G of 3/4 plus IT, an easy bound is less than Q to the 1/4, 1 plus T. Yes. That you should be able to get. And with that, it tells you that this one is big O of Q to the 1/4 upon X to the 1/4. Q to the 1/4 upon X to the 1/4. Since it's not Q, it's K, sorry. My conductor is K. You know, it's because in the large sieve inequality, I have Q everywhere. So I say for the fixed arithmetic progression, I take K. But usually I'm using Q, so sometimes you'll see in my notes, you have some Q that pops in. So it's okay here, it's okay. You know that L1 chi, since L1 chi is larger than 1 upon square root of K, okay? If you take, we take what? X equal K to the, okay. We want X upon K to the 1/4 to be strictly larger than 1 upon square root of K. That's what we want. So we need X to be larger than yes. That was confusing. K square, K cube. Okay? So we take X equal K4. X equal K4 means I get L1 chi plus a little o of L1 chi larger than 1 upon log K, which is what I wanted. Okay? I've always thought that maybe it would be possible to look a bit better in this argument and maybe get a bit better than 1 upon log. Because finally we believe that we should be able to do log. So maybe even beating the factor 2 gets even better than this one. If you want to try, because there's quite some loss here between this one and that one. We forget quite a number of guys, but it's just for you to think. I'm not going to give anything more. Tomorrow, I'll give another proof of the advantage margin inequality because that's my team. And it will be a proof that uses the circle method. I mean, circle method in a very mild way. Thank you. Mm-hmm.
Is there any problem for problem session?
The problem for the problem session is, is it possible to improve? I'm not sure, you know. Getting something just a bit better than this log would be rather impressive. Aha. Yes. No, but yeah. Yes. No, but it's maybe if you look at this proof, you can get a bit better out of this proof. I'm not sure. maybe you can get a bit better out of this proof. It's not clear because x is very small. It's only a power of k. But maybe you could twist this power to go a bit farther, a bit higher power, but save more on the upper bar, on the upper part. That would be well, something new in this area. Thank you.
We have a coffee break now, right? For 15 minutes. Yeah, we'll come back at 4:15.
That's the end of the piece.